Hello. Am I audible?
Hello.
Yes. Am I audible?
Yeah, you're audible.
Thank you. So I welcome you to the today's session of fundamentals of theoretical and experimental aerodynamics. Uh, Professor Arnav Roy is the instructor of this course from the Department of Aerospace Engineering, and I am Gangadhar Venkatramana, a teaching assistant. Today we are solving two problems from the session that we left in the last session. So without any delay, we can start the today's session. So just let me give a small recap of the last session details. I hope this session is recording. Yes. Okay. So yeah, in the last session we seen few problems related to this supersonic flows that are also high-speed flows, and that we solved a few problems on nozzle, convergent, divergent nozzles, and related to shock wave, normal shock wave, and oblique shock wave problems. And we will see the remaining unsolved problems that we left with. So this question is also related to the enthalpy, the amount of energy, and yeah, regarding the compressor. And these are all few questions that we solved in the last session. And let's see the remaining questions in this session. So the question states that which option is correct for the following statements? We have two questions that two statements, that is, when supersonic flow is turned into itself at a compression wave, it forms a normal shock wave. That is, the question is stating that supersonic flow is coming in the free stream, and here is this supersonic flow is now turning into itself. That means if it is flowing over a wedge and turning into itself, like it is turning into itself. Then the statement is saying that a normal shock wave will form at this particular turning location. But according to this, when a supersonic flow is turning into itself, we see an oblique shock wave. It is not a normal shock wave. So the first statement is false. Okay. And second statement is when supersonic flow is turned away from itself, it forms an expansion fan. Yes, this statement is true. The supersonic flow is when it is turning away from itself, like this. We can see expansion fan where the expansion waves at this corner. These we call as expansion fan. So the second statement is true. So this is the solution. Like first statement is false, then second statement is true. This is the solution for this question. Okay. Let's go to the next question.
So that's one.
Yes.
So if it is only supersonic flow, we'll be having expansion flow and shock waves, right? What will be the case if it is a subsonic flow?
In the case of subsonic flow, you don't see this kind of behavior because in the subsonic flow, your
Sonic
information
condition
can.
at least.
Sonic condition is the transonic condition, that is entirely different theory. We always look at subsonic either or supersonic. In the subsonic
So
case, yeah,
in the subsonic flow, if the flow is moving away from its path, so will there be what type of, I mean, will expansion fan will be available ex- or not? Uh,
expansion can occur. Expansion can occur, but it is not an expansion fan. Expansion is different from the expansion fan. Expansion fan where finite waves uh, are developed in the flow field, and that is causing a significant change of properties, pressure and density across the fan for every finite wave.
okay. I mean, in whether any type of shock wave can be possible in subsonic flow. I mean, is there any possibility of forming any type of shock wave at least in a subsonic flow?
No, there are no finite waves possible in the subsonic flow, but you can see the waves like which are not a finite, but acoustic waves are possible, where the information is passing through that acoustic waves.
Okay, thank you,
Yeah.
sir.
Okay. So let's go to the next question. So in this question, we are having uh, where is there a chance of obtaining a normal shock for the flow? Let me take it. For the flow depicted in the graphic below. We have a blunt body here, or you can say it's a bluff body. And because of the incoming flow is supersonic, the incoming flow is supersonic, we are seeing a bow shock here. So in this bow shock scenario, we can approximate some particular region. We here in this question they are marked as region 1, region 2, and region 3. Three regions they are marked, and the scenario is symmetric because the body is also symmetric. So you have same region 3, region 1. So they are asking it at what region we can expect this bow shock behaves like a normal shock, that is corresponding to region 2. So at region 2, very small area, not the entire one, very small area can be approximated with pulse shock wave characteristics. Okay, so this is the solution for this question. So we can approximate the bow shock, and near the leading edge, there you can say the properties are similar to the normal shock wave. So coming to the next question. So in this question, we have which of the following is uh, which of the following is an incorrect equation. Here they are asking for the incorrect equation, not for the correct equation. So let's see these equations. Like these equations are applicable, they are saying for the normal shock wave. So let's find which equation is not applicable for the normal shock wave. Let's see the first equation. First equation is stating that incompressibility. This equation is for the representation of incompressibility of the fluid, or also continuity equation for constant density, steady state fluid flow. So this del dot V bar, the divergence of velocity field, is the representation of purely the incompressibility of the flow. So also it can be approximated, or also it is a representation of the continuity equation, the mass continuity equation at the assumptions of constant density and the steady state flow field. So let's see the similar things for all the equations, and then we can say which equation is not applicable for this normal shock wave. So in the second equation, if we see, it is rho 1 u1 equals to rho 2 u2. This is continuity, one dimensional, continuity, one dimensional, steady state, constant area. This is continuity equation, mass continuity equation, but it is a one-dimensional, and it can be applicable. It is applicable for the compressible or incompressible flow, or constant density or variable density flow, because you have rho 1 and rho 2, two different densities. So this is one, and this is momentum conservation. Again, one dimensional. And the last one is energy conservation. Also one dimensional. So these are the four different equations given in the options. When we see that all these option B, C, and D are applicable for both compressible and incompressible flows. These are applicable for both the compressible and incompressible flows. Whereas the option A is only applicable for incompressibility. It is clearly the equation for the incompressibility of the fluid. When we try to apply any equation for the normal shock wave, that should be the first primary condition. It should be compressible. The equation should consist of, or it should able to handle the compressible terms in the flow field. So this option is incorrect. This is not a suitable equation for handling the normal shock waves. Okay. Yes. Let's go to the next question. Okay. In this question, we have, which of the following describes flow of calorically perfect gas? Calorically perfect gas, where we are maintaining our Cp and Cvs are as constant and or only as a function of the temperature. So across, not a function of temperature, they are only constant values, Cp and Cv, where the specific heat at constant pressure and the specific heat at a constant volume. So across a normal shock wave, uh, we need to identify how these parameters or which of these options are correct. Whether, like, let me clearly pictorially represent that. If this is the normal shock wave, and we have the properties flow above and upstream or downstream, we say. So in upstream, we can say it is a region 1. The downstream, we can say it is region 2. So at the upstream and downstream, we are having these flow properties, and this is a normal shock wave. So the question is having few parameters. Let's discuss only those parameters. That is U. This is U1, U2, and this is M1, M2, P1, P2, P01, P02, T1, T2, S1, S2, Rho 1, and rho 2. This is the velocity. Since it is one dimensional, we are considering only the u component. And this is the Mach number. This is the static pressure. And this is stagnation pressure. And this is static temperature. This is entropy. And this is density. So these are the properties given in the question. So let's find the correct answer based upon this normal structure properties. The upstream velocity u1 is always greater than the downstream velocity. So u1 is greater than u2, and the Mach number, the upstream Mach number, this is upstream that represented with the letter 1. This is downstream. So the upstream Mach number is always greater than the downstream Mach number, where the point I should mention here, this is always supersonic, and the M2 is always subsonic. This is it's a universal for any normal shock wave. The upstream is supersonic and downstream is subsonic. And then static pressure. The static pressure after the normal shock wave always increases. So static pressure is always increases after the normal shock wave. And at the same time, the stagnation pressure, because of the loss of the stagnation pressure, the stagnation pressure in the downstream decreases. And the static temperature always increases after crossing the normal shock wave. And then entropy. Entropy is all the same. Entropy increases always across the normal shock wave. And the density also increases across the normal shock wave. So this is the correct formation for this question. And these, let's see the far correct option for this is the option B, that is having all these properties of related to normal shock wave. So we should remember these symbols that and its indications while solving this kind of problems. That 0 indicates here, this not indicates the stagnation properties. The symbol that represents the stagnation properties. There is no not, then it represents the static properties. Okay, fine. So let's go to the next question. So in this question, we have a problem of, let me read this question and then we can discuss about it. So we have a nuclear explosions shock wave. A nuclear explosion shock wave. The shock wave is traveling at a speed of 12,000 meters per second. That is approximately 12 kilometers per second. And it is propagating into still atmosphere. So let me just, this is the normal shock wave. This is still atmosphere. This is propagating at the speed of, that is, we are having u1. Let me not write this u1. Say shockwave velocity. Let me just write it as a 12,000 meters per second. Then we can uh, analyze it. Then we can, while analyzing or finding of the solution, we can indicate its letters. Okay. Yeah. Still atmospheric here with a pressure of 1.01 into 10 to the power 5 newtons per meter. So here the atmospheric pressure is say P, will just indicate this P atmosphere or P1 is equals to 1.01 times 10 to the power 5 Newton per meter square. This is 12,000 meters per second. And the temperature is also, say this is T1. This T1 temperature is 298.15 Kelvin. And the question is calculate the stagnation pressure and stagnation temperature values in relation to the stationary. We need to find out stagnation pressure and stagnation temperature values in relation to the stationary observer after the shock crosses the location. So here we need to find out the T02 and T02. We have some more information of this T02 and T02 because they are asking for the stagnation properties, and that is in relation to it. Like the analysis is always in the perspective of normal shock wave. Like here we are considering the realistic problem as the shock wave is moving, but the scenario is we actually move the uh, uh, fluid crosses the shock wave at the velocity of what normal shock wave is propagating. Like instead of shock wave, this is like a person sitting on the shock wave and traveling with the shock wave. That person, whatever that person feels, we are analyzed always in that perspective for our simplifying the flow field and mathematical analysis as we derived for that. Okay, so let's handle the remaining equations or remaining data given in this question. That remaining data is in relation to the stationary observer, and after the shock crosses the location, we have the gamma equals to specific heat ratios, gamma equals to 1.4, and universal, sorry, the specific gas constant is 287 joules per kg Kelvin, and yeah, and further the non-dimensional or dimensional properties that were M02 equals to 0.338, then T2 by T2, that it is corresponding to some Mach number. These two corresponding to a Mach number, that is a supersonic Mach number and subsonic Mach number. So whatever the data we will be getting, either it will be M02 that represents a supersonic Mach number or represents a subsonic Mach number. So we have to identify whether we are getting the flow behind this normal shock wave is supersonic or subsonic, and then we need to identify its corresponding Mach number. Definitely, like we need to see whether it is really supersonic or subsonic. If it is supersonic, we have to apply the relations of T2 by T02 for these relations, or else we need to apply the secondary relations, these relations. This is the first one, this is the second one. So apply using this, we have to find only the T02 and P02, the values we need to find. So let's start our analysis. Consider this area, that is a still atmosphere, as a region 1, that is upstream or ahead of the shock wave, and the region 2 is behind the shock wave, that is the downstream. Okay, so let's assume a person is sitting on the shock wave, but the real problem is stating that the shock wave is traveling at a speed of almost 12 kilometers per second or 12,000 meters per second. But let us assume in such a way that this shock wave is standstill in some particular location in air. When we consider in this way, like in the perspective of normal shock wave, what we will get? We will get, let me clearly write it. A flow is coming at a speed of U1 equals to 12,000 meters per second, and its P1 equals to 1.01 times 10 to the power 5 Newton per meter square, and T1 equals to 298.15 Kelvin. So a flow with these properties are crossing this normal shock wave and will convert into some other properties. So let's find out the Mach number uh, ahead of this normal shock wave. How we can find it? The Mach number M1 is equals to the speed of sound by, sorry, the speed, local velocity of the fluid by the speed of sound, that is A1, V1. So M1 is equals to V1, we have 12,000 by square root gamma r T1. Let's substitute the data. This is 12,000 by square root gamma we have 1.4 and r we have 287. We don't need to worry about the units because all given in the same units. So, and the T1 we also have in Kelvin, that is 298.15 kelvins. So if we solve this, we will get the upstream Mach number as M1 equals to, let me show you that, yeah, 34.67. The Mach number is a non-dimensional parameter, so you won't get any units to this Mach number M1. And if you like solve, you also solve this particular denominator, that is the speed of sound, A1 you will get around 346.12 meters per second. This is the speed of sound, so you will have the values. So let me write these things here. M1 equals to 34.67 and A1 equals to 346.12 meters per second. Okay, so this is the data we have now. Using the normal shockwave relations, now we can find the M2 and the corresponding velocity U2 behind this normal shockwave. So what is the normal shockwave relation that we have, that to find out the Mach number um, behind the or in the downstream of the normal shockwave, that is M2 square equals to, let me write the equation, uh, M1 square plus 2 over gamma minus 1 by 2 gamma over gamma minus 1 M1 square minus 1 and over 1 by 2, power 1 by 2. So this is the equation to find out the Mach number in this region, that is M2. M2 is the first query that we need to find out. So to find out this M2, what we need to do, we need to substitute the M1 and gamma values. So let's substitute that values. We have M1 equals to 34.67 square plus 2 by gamma equals to 1.4 minus 1 upon 2 times 1.4 upon 1.4 minus 1. M1 square is 34.67 square minus 1 and over 1 over 2. So this is the substitution. Let's simplify this. If you simplify, you will get 34.67 square plus 5 over 734.67 square minus 1 and whole over 1 by 2. So the final value is M2 equals to, so this is not M2 square. The final M2 value is 0.38. You see, the relation is stating that if your Mach number is around 34.67 M1, you will get M2 equals to 0.38. It is really a huge change when you compare uh, the upstream Mach number and the downstream Mach number. The M1 is around 34.67, where M2 is around 0.38. So Mach number less than 1 is subsonic, and the criteria is in the downstream of the normal shock wave, we should get the subsonic Mach number. So that is what we obtained from this relation, and it is clear that we are going in the right way. And the second thing is, since we obtain now M2, we need to obtain the static temperature at that particular location to get velocity at that location, because we need to obtain the velocity at this particular downstream of the shock wave. Using that velocity, again, we need to convert into the stationary frame of reference. Now we are actually, this is shock wave. This is shock wave frame of reference. That means shock wave frame of reference means that we are traveling, or the analysis that we are doing is with respect to the shock wave. That is assuming the shock wave is stationary and the flow is moving. Shock wave frame of reference. where this is stationary frame of reference or inertial frame of reference. So these two frames we have here, that is shockwave frame of reference and stationary or inertial frame of reference. Now we should remember and we should keep in mind that we are doing in a shockwave frame of reference. In this shockwave frame of reference, we just calculated the Mach number downstream of the shockwave. Now we need to calculate its velocity of the flow in the downstream of the shockwave. For that, we need the temperature T2. So how we can find out this temperature T2 using the shockwave relation? So for that, we can use a particular relation of this normal shockwave, that is T2 by T1. Let me write this whole equation so that you will be able to understand this. 2 gamma over gamma plus 1 m1 square, where m1 is the Mach number ahead of the normal shockwave. Gamma minus 1 over gamma plus 1 plus 2 over gamma plus 1 m1 square. So this is the relation of T2 temperature and T1 and T2 temperature ahead of behind of the normal shockwave. So we have only a parameters in this RHS is the Mach number ahead of the shockwave, that is M1. So let's substitute all the remaining things. When we substitute and simplify this, we will get 1046.18 times 0.17 plus 2 over 2.4 times 34.67 squares. And further simplifying, you will see it is 240.03. Okay, now we have T1 here, but what we need to get is T2. Okay, that is temperature T2. We got the ratio of T2 by T1 equals to 240.03. That is the temperature ratio. We can see the Mach number is so high and the temperature is around 298.15 at head of the shock wave. The moment it crosses the shock wave, we are changing around 240.03 times the temperature is changing. That is very huge. That is not even addition or additive of the temperature. That is just multiplication, the times of the change in temperature. So T2 equals to 240.03 times. What is your T1 temperature? T1 is 298.15. Then let me write what is the value of this T2. The value of T2, even here, let me calculate for you, is 240.03 times 298.15. You will get around an unusual temperature, that is 71,564.944 Kelvin. This is very huge temperature to handle it. So it is just for your understanding. It's not a completely realistic problem, but this is a general scenario to calculate the properties across this normal shockwave. So now we are at the calculation of T2, but we need to get first U2 in the shockwave frame of reference, and then we need to convert into the U02, that is in the normal stationary frame of reference. So let's calculate the U2. Just let me come out of this. So just add one more slide here. Give me a second. Yeah. So now we have all the required things, that M2 is equals to 0.38 and T2 we get is around 71564. 71564. Okay. So some decimal points is there, that is Kelvin. Now what we need to do is we need to find out the velocity u2 from the uh, which refers the Shockwave frame of reference. So u2 can be like this. So the u2 is, just give me a second. Okay. So the u2, how we can find out? Let's write the Mach number relation that m equals to m2 equals to u2 over square root gamma r t2. This is the relation of our Mach number. So from this we can separate our t2, that is m2 times square root gamma r t2. Let's substitute the values what we have. Gamma is 1.4287 times 71564. And then once we simplify that, we will get u2 equals to around 9,962 point. Sorry, this is not the correct one. You will get u2 equals to where is it? Yeah, 2037.69 meters per second. So if you simplify this, you will get the u2 value equals to 2037.69 meters per second, where our u1 is, I hope you can recall the u1. u1 is around 12,000 meters per second. Our u2 is 2037 point. It is changing the very huge velocity across this normal shock wave. We generally call these kind of normal shock waves as a very strong normal shock waves. So these strong normal shock waves can able to change the properties in very severely and affects the temperatures of the coming fluid or wherever it's traveling in the flow field. So these strong shock waves has a significant role in various applications in the field of aerodynamics or in the field of medicine. In several fields, this is priority of using the shock waves. Even in the gas industries, also the strong shock waves are like has been employing for condensation process. So u1 equals to 12,000 and u2 equals to 2037.69. And one more concept is here. Until now, we are solving in the uh, Shockwave frame of reference. That is, let me write it clearly here. Shockwave frame of reference. When we see the things in the Shockwave frame of reference, here the flow has a velocity of 12,000 meters per second. Okay, and here the flow has a velocity of 2037.69 meters per second. Okay, and the velocity of the shock wave is, I just want to indicate it like this: velocity of the shock wave is 0. Okay, so velocity of the shock wave is 0 meters per second. This is the shock wave frame of reference. Now we have to convert this into such a way that in the stationary frame of reference, to the stationary frame of reference, in this stationary frame of reference, what we need to do is this shock wave should get the velocity of 12,000 meters per second. Everything should be in the relative sense. That means if the shock wave is acquiring the velocity of 12,000 meters per second, our u1 should be equals to 0, because we are now in such sorry, uh, removing or subtracting the 12,000 meters per second from all the velocities in the Shockwave frame of reference to change it to the stationary frame of reference. So when we subtract the 12,000 from this, that is 20, note that the flow velocity of these two, u1 or u2, are in this direction. So in the same way as we subtracted the 12,000 from u1, you will get u1 equals to 0 here, or this I can say for indication or different letter u01 equals to 0. Now I am calculation of u02, that is 2302.69 minus 12,000. Now my flow will be in this direction. So whatever the value is, because it is a negative value, so your direction will change. That is U2 will change into this direction, that is U02, and that value is 9,962.31 meters per second. Got it? So this is our U02. Okay. Since this is in a relative sense, the properties or now we cannot judge the properties directly uh, as we are seeing. We need to calculate still the T02 and T01 based upon this value, this 9,962 instead of this 2,037. That is what they ask in the question. So now you have U02 is 9,962, but with respect to the question, the data they gave for M02 or M02. So we need to find out the M02, that is correspond to the Mach number of the particular uh, flow velocity that crosses the shock wave. So how to find out the M02? M02 is again equals to U02 by T2. Note that it is T, sorry, this is not T2, this is A2. We need to use the sound velocity. So to calculate M02, what we are doing here, using this velocity, that is 9,962.31 over square root of, or we already solved this A value, that is here. This is the A value of it, and that is equals to around 5,362.35 meters per second. So just let's use the same, that is 5,362.35. So upon the division of this sound velocity and flow velocity and the sound velocity, we will get the value as 1.86. That is M02 with respect to the stationary frame of reference. The Mach number is 1.86. That is supersonic. What we can understand from this, from the stationary frame of reference, the shock wave can generate a supersonic flow on behind of it when the flow is like when the shock wave is moving with this particular high speeds. Okay, so it is now generating a Mach number of around 1.86 in the behind the shock wave. So from our given data, if we get M02 is equals to 1.86, we have the data like T2 by T02 is equals to 0.58 and P2 by P02 is equals to 0.15. We already calculated the value T2. We need to find out the T02. So this is the only unknown here, but we did not calculate the value P2, but we need the value P02. So let's find out the P2 first. We again can use the Shockwave relation, that is P2 by P1 equals to 2 gamma by gamma plus 1 M1 square minus gamma by gamma minus 1 by gamma plus 1. When we simplify this, we substitute all the details of it. When we simplify, we will get 1.17 times 34.67 square minus 0.17, and that is equals to 1406.18 P2. So we have P2 here, that P2 value is ambient atmosphere. That ambient atmosphere, when we multiply that, we will get a huge static temperature, high value. That it is again also not realistic for the calculation, but it is just for our understanding. So 1420.24 times 10 to the power 5 Newton per meter square. So this is our P2 value. This is P2. So what we need to get, the final thing is we need to obtain the P02. This is the one we need to obtain. Okay. So to calculate the P02, and the second thing is the T02. So let's use these relations. P02 is equals to P2 by 0.15, and T02 equals to T2 by 0.58, where we just got the P2 equals to 1420.24 times 10 to the power 5 Newton per meter square, uh, by 0.15, and T2 we got the value of T2 is 71564 by 0.58. Upon simplifying this one you will get the T02 as 1,23,387, 123,387 kelvins. This is very high temperature, not a realistic one. And also the P02 you will get 9468 times 10 to the power 5 Newton per meter square. So these are the solutions of this problem. So what we just did in this entire content is, let me show you the question, and like the question is here itself. I'm going to turn the things. What we did is, first we started with the question given in itself in the stationary frame of reference. In the stationary frame of reference, we have an ambient temperature here. In this ambient temperature or ambient air, your velocity is zero. I mean, I'm only talking about the flow field here in this particular region. There won't be any velocity of the flow field, but a normal shock wave, which is a very strong shock wave, which can change the properties in a huge, with a huge difference ahead and behind of it. So that is traveling with the speed of almost 12,000 meters per second into this ambient air. So when it is traveling or crossing this with this particular velocity, we calculated that it can induce a velocity of approximately 9,962, that is 9 kilometers per second. I can say this much of velocity it can induce uh, behind the normal shock wave, and that travels along the shock wave. So this is what happening in the stationary frame of reference. But to calculate this value, this induced velocity by the shock wave, what we did, we transformed into the Shockwave frame of reference. What is this Shockwave frame of reference? Assuming the shock is stationary in the flow field and the flow is moving into the or onto the shockwave, or it's passing through the shockwave with such that the shockwave velocity is stationary. That means your flow should get the similar velocity, that is 12,000 meters per second, the head velocity. So the relatively it is the same thing that what we are doing here and what we are transforming here. So with this velocity it is coming, and if the shockwave is stationary and the flow field is coming with this velocity, in the downstream you will get a U2 of 2000, that is 2 kilometers per second approximately. So this is the velocity that you will get in the downstream if the flow is moving. This is the difference we need to observe clearly. When the shockwave is stationary and the flow field is coming on to the shockwave, then you will get the flow velocity around like the flow velocity flow still moves in the downstream. So in this direction, this particular direction, and its velocity is different than the head velocity or the upstream velocity at 12,000 meters per second, and the shock wave is still stationary. At the same time, if the shock wave is moving and the flow field is stationary, it induces a velocity that travels along in the direction of the shock wave. So this is the kind of analysis, because why we did this kind of analysis is all those equations that we derived from the past derived for the stationary kind of shock wave. So to handle the velocity, we have to use the correct frame of reference, because the equations were derived for the stationary frame of reference. If it is a scalar value or some kind of thing, still we need to use that correct frame of reference in which the equations are derived. So for that particular purpose only, we transform, though the problem is given in the stationary frame of reference, we transform it to the Shockwave frame of reference. And then we calculated what is this particular velocity induced by the shockwave in the stationary frame of reference. Then we calculated the Mach number corresponding to that. This is the Mach number corresponding. This is, we found it is a supersonic Mach number, that is Mach number greater than 1. or the supersonic flow. And then we identified what is its P02 and P02. That is what stagnation properties, stagnation temperature and the stagnation pressure. Okay, so these are the properties we identified for this particular problem, and the solution is these values, that is stagnation temperature and stagnation pressure. So we got this solution. So after obtaining this solution, what is the caution, or what is the note point? Like I can say, all these values are not a realistic values. These are the for your understanding purpose that we derived this. We given these kind of values, but even it is correct values, this is the process that we have to follow to obtain the stagnation or whatever the properties that we calculated in this entire problem. So I hope you understood this question. And before going to the next question, we can just have a 10 minutes break, and we can uh, meet again at 7:05 p.m. Okay, thank you. I hope you are all back. So welcome back to the session after the break. Let's continue to the next question. Uh, yeah, take a pen. So this question now regarding a nozzle. We have a nozzle is connected to a large tank. The nozzle connected to a large tank in which the air is stored at pressure of 2 times 10 to the power 5 pascals and at 10 degrees. Let me draw this for our schematic purpose. So the tank is consider this is a tank of a very large tank just for a schematic purpose I'm drawing it. And then it is connected to a convergent divergent nozzle. This convergent and divergent section. So once we connect it to it, the question, the pressure inside this tank, the stagnation pressure that we say as P naught, is P naught equals to 2 times 10 to the power 5 pascals. Okay, and then and the temperature T naught is equals to 10 degrees Celsius. This is the given data. And it is noted, it is given that air expanded isentropically. I think I'm audible, right? Am I audible? Yes, I'm audible. If it is not audible, please let me know. Okay. So the T naught temperature inside this tank is 10 degrees Celsius and expanded isentropically. Note that the condition it is expanded isentropically, so we can use the nozzle relations with isentropic assumption and then through the nozzle to atmosphere. This is given atmosphere temperature, that is 1.01 times 10 to the power 5 pascals. You can take it as an atmospheric pressure. We generally say it is PE, that is P exit, and then gamma is as usual given as 1.4. We need to find out the temperature at the exit of the nozzle. So what we need to do is we need to just find out the temperature at the exit of the nozzle. What we have the pressure difference between inlet and exit, that is 2.5 to 10 to the power 5, and then we just have the temperature at the inlet, but we need the temperature at the exit. For this, what we need to do is we just first need to calculate the Mach number because it is an isentropic. We can use isentropic relations and we can calculate the Mach number at the exit of the nozzle. So for that, we can use, say, ME is Mach number at the exit of the nozzle. And if we use the isentropic relations, note that the temperature given is 10 degrees Celsius. We have to transform that to the Kelvin, that is 283 kelvins. Okay, and the pressure ratio across the nozzle, stagnation to static, that we can write as P naught by PE is equals to 1 plus gamma minus 1 by 2 ME square times, sorry, power gamma by gamma minus 1. We have P naught here. We need to find out the, sorry, we have PE also, that is pressure at exit. We need to find out the ME. So the ME, once we simplify, we will get ME equals to 2 over gamma minus 1 times P naught over PE power gamma minus 1 over gamma minus 1 the root. Okay, so let's substitute the values that we have. We can simplify for the Mach number at the exit. Why we are simplifying for the Mach number at exit? To find out the temperature at the exit. We have an isentropic relation between the Mach number and the temperature, or we can directly substitute the temperature equation also. It is just the same inside this power. This is the temperature ratio equation isentropically, but we are just doing in a conventional way, and that equals to 1.01 times 10 to the power 5 power 0.4 over 1.4 minus 1 whole to the power 1 by 2. This will give you a Mach number at the exit of the nozzle is equals to 1.04. Okay, so this is the Mach number at the exit. And what is the relation for temperature ratios? That is T naught by T exit, T naught by T E equals to the same inside this power, that is 1 plus gamma minus 1 over 2. Note that there are Mach number at the exit is a supersonic. You should identify the characteristics also. So it is better to recall this whether we are dealing with the supersonic flow, subsonic flow, at what are the where are the locations we are dealing with is also important to recognize all the times while solving these kind of problems. Because some cases you can identify easily whether you are getting a correct solution or not. In the last problem also we've seen that there's a shock wave is creating a subsonic flow if the flow is like from the supersonic flow to the subsonic flow. So while you're calculating, you're getting some kind of supersonic value behind the normal shock wave. You can verify that instead of directly uh, uh, putting the value what we get, we can just verify whether it is correct or not by understanding the physics of it. Okay, so in that way, we see that the flow at the exit of the nozzle is a supersonic flow. That means definitely there should not be any kind of shock present inside the flow. So let me substitute the same values because we need to find out the TE. This is our requirement. So if I put the values of gamma and Mach number at exit, you will get 1.392 as a ratio of T naught by T. This is the ratio of T naught by TE. So once you find the ratio of T naught by TE, you can write it as TE equals to T naught over 1.392. That is equals to 283 by 1.392 is equals to 203.30 Kelvin. But what we need the like the solution is also in the Kelvin, so we need not to convert into the Celsius. So as I said earlier, we have a cross verification here whether our value is correct or not. We can find that we have the initial temperature as 283 Kelvin, that is a T naught, and the relations are isentropic, and we are looking for the temperature at the exit, and the flow having a velocity of supersonic, the supersonic velocity or the Mach number related to supersonic, that is 1.04. So it's not a blind, but it is a theory. Once you understand the flow characteristics properly, you can estimate that definitely the temperature should be lower than the 283 Kelvin, somewhat below the given temperature 283 Kelvin. It can be either anything that under the 283. So this is not the option. In this way, we can eliminate the options very easily. And then since there is no heat exchanging kind of phenomena or anything, so reaching the very closest possible temperature, that is 287, because the flow at the exit is supersonic, and because it is much of low temperature or low pressure it should reach. So reaching between these two temperatures is also not logical. So because 283 and 278 is very close, so it is also not logical uh, to reach the supersonic flow with very small temperature difference. So definitely it should be somewhat lower temperature. Either it should be 230 or 203. So in this way, we can eliminate the options that we have in the question, and we can simplify our uh, process that we are following. We can easily identify the correct solution in the short time. So this is a way, but it is the usual process for solving the assignments. You should always use the equations and take the values of it, and then applying the physics. What actually really happened, you need to understand. That is the correct way while solving the assignments. But for the competitive kind of way, you have to first pick out the options. If you have, if there are options available for you in the competitive kind, you can pick out the wrong options and choose the and select the correct one. That is also you can see that feasibility in this question. Okay, so let's go to the next question. Here again we are having a normal shock wave problem. So in this normal shock wave, we have, say, this is a stationary normal shock wave that is in the frame of reference of normal shock wave only, because they did not give any values of it. So if the upstream Mach number is 1.5, what is the Mach number downstream of the normal shock wave? It is just a direct substitution of values in the Mach number relation across the shock wave. So let me just draw the things. So if you have a shock wave like this and you have a Mach number m1 in the upstream, that is m1 equals to around 1.5. Note that the given value is 1.5, that is supersonic. So supersonic only you can get the normal shock wave. So once the flow crosses the normal shock wave, the m2 becomes subsonic. That is m2 is question, but m2 we definitely know that m2 is always less than 1 uh, behind the normal shock wave. That is subsonic flow. So to calculate that, let's directly go for the Mach number relation. Across, let me write the equation for you. And that equation is m2 square is equals to 1 plus gamma minus 1 over 2 and m1 square over gamma m1 square minus gamma minus 1 over 2. So this is the relation of Mach numbers across the normal shock wave. We have now m1 here. It's a direct substitution. We need to find out the m2. So to find out the m2, let's substitute the things. That m2 is equals to m2 square is equals to 1 plus 0.4 over 2, 1.5 square upon 1.4 cross 1.5 square times 0. So minus 0.4 over 2. So for all after the simplification, we will get this m2 square equals to 0.49. This is m2 square. We need to get m2, that is the Mach number behind the shock wave. That is around 0.7. m2 equals to 0.7. m1 equals to 1.5. I have to mention two things here. It is very clear that m2 is less than 1, and we got the m2 as a less than 1 itself, that is subsonic. So it is proven that always the flow behind the normal shock wave in the stationary frame of reference, or from the normal shock wave frame of reference, the flow is subsonic. So it is clear from that subsonic, supersonic. But I need to mention one more thing from the previous problem time that we solved in the previous problem also. A normal shock wave we solved there, M1 we have around 30 approximately. Since I can say 30, M1 equals to 30, the Mach number, the supersonic Mach number is around 30. But at that we got the M2 equals to around 0.3. It is approximately 0.3. I can say it is not equal to, it is approximately. So the difference we see for the 30 Mach number, approximately 30 Mach number, we are getting an M2 of 0.3 approximately, even though it is very high supersonic high Mach number. But when we see the M2 equals to 0.7, sorry, M1 equals to 1.5, that is very less compared to this supersonic value. Compared to this M1 equals 30, this 1.5 is very less. But we got the value of the flow, the downstream of the shock wave is just 0.7. But for the high supersonic flow value, we got the Mach number is 0.3 behind the shock wave. Why? The reason is for high supersonic values or at high supersonic flows, you will get a strong normal shock waves. Strong normal shock wave. Even we can see that the same from the relation of this adiabatic assumptions that we generated the result for the Mach number relation ahead and behind the normal shock wave. From that also we can observe that if M1 is as large as much as more, you will get M2 at such low value. If M1 increases, your M2 always decreases. In this way, the relation is stating that. So that's why if you have a very large supersonic value, you will get a very small subsonic value. If you have supersonic value but close to related to 1, I mean approximately in the low values in the supersonic levels, you will get a subsonic of high values of the flow. That is some kind of, it is still a strong, I mean, still a normal shock wave, but it is not as strong as this normal shock wave. Okay, so this is all a different story. Let me mark with some other color. Just write it is from which problem it is. It is from problem 10. So this we took from the problem time. It is not related to this question, but just for your understanding, I framed this. So hope you able to understand what is this Mach member relation and how it is handling across the normal shock wave. So if that is the case, let's go to the final question of this particular presentation. The final this question stating that, let me read the question and then we can move forward. This question is stating that assume that uniform supersonic stream. Again, we are doing some shockwave problem, but it is not a normal shockwave because nowhere it is mentioned as a normal shockwave. We are just having a supersonic stream that is uniform, having a Mach number around 3, is deflected by compression corner. We seen already what is this compression corner at the beginning of this lecture or the beginning of this session. This is what we say as a compression corner. So the flow turns into itself because of this compression corner, and it is an angle at an angle of 30 degrees, producing a shock at an angle of 52 degrees. This is a shock wave. This is not a normal shock wave. This is an oblique shock wave. And this shock wave is having an angle of 52 degrees. The question is now calculate the Mach number downstream of this shock wave. So here you have a flow of M1 is equals to 3. And here you have a flow of M2 equals to question. That is the question we have. So how to calculate this Mach number? We don't have a relation that is particularly for a oblique shock wave. Oblique shock waves can be any angle, so there can be different possible angles of oblique shock wave can be formed. But how to calculate that? The theory says that we can transform this oblique shock wave, we can relatively resolve the velocity uh, perpendicular to this oblique shock wave and oblique shock wave line, and then we can treat that velocity is crossing a normal shock wave. So what does it mean? What does it mean is now this flow is passing through a particular oblique shock wave which is at an angle of 52 degrees from the horizontal or the flow direction. So we can resolve some particular component. This is a velocity. We can resolve a component in such a way that that component of the velocity. So this is not correct. Sorry, just a minute. Yeah, sorry for the interruption. Uh, let's share my screen again. Yes. You can resolve these things. Okay, we can resolve these things uh, in the way perpendicular to this oblique shock wave. When it is perpendicular to the oblique shock wave, at this property, like this amount of velocity is nothing but it is facing a normal shock wave. So we have to resolve that velocity or the Mach number we can resolve, and then we can apply the resolution of the forces, resolving of the force, like not forces, resolving of the velocity by using the sine or trigonometry relations, and then we can get uh, the Mach number. Let me clearly draw this for you. If this is the oblique shock wave, take one more. This is the oblique shock wave, and this is the flow coming with the Mach number m1, and we resolved it uh, in the direction. We resolve it in the direction perpendicular to the oblique shock wave. So when you resolve this direction perpendicular to the oblique shock wave, this particular velocity will assume or it will act as a flow passing through a normal shock wave because we resolve this particular velocity into the perpendicular to oblique shock wave. So this changes. Uh, we can now apply the oblique shock wave relations, and again we can transform into the way that see, because here we see. Let me take one more color. Just yeah, this wall. This is the wall or the compression corner we are talking about. Okay, this now makes our problem difficult compared to the normal shock wave. I will take this. This again you can resolve in this particular way. Because flow always travels in such a way that it always follows the solid objects, because here it is following the solid object horizontally, and here also it should follows uh, the path or follows this particular what we say this particular wall. So our flow also travels in this particular way, and then resolution we can again using the trigonometry we can follow. We can calculate this particular value. The target is to find out this particular M2 value. But what we need to do is we need to transform this M1 that is corresponding to uh, normal to this oblique shock wave, that I can say M1 component N and M2 and component N. What is this component N means? This is the component N that is normal to the oblique shock wave. So what is that component normal to the oblique shock wave? Using the trigonometric relations, that we can find that M1N is equals to M1 sine of beta. What is this beta? I need to mention here. This is your beta, where the oblique shock angle. This is your theta. We have now beta equals to, given that beta equals to 52 degrees and theta equals to 30 degrees. Okay, so we are now transforming it into the oblique shock wave normal direction, as we have this particular angle here is beta, that is again nothing but this particular angle, isn't it? Yes, this angle. So this angle is again your beta. So to find out this component, you need to use a sine, that is M1 sine beta. Let me write it clearly. So this is now the normal component. So using this, we can find out the M2N. That is, I can say M2N. I can just directly substitute this in the normal shock wave relation as 1 plus gamma minus 1 over 2 times M1 normal component square. This is also square here. And then gamma M1 N square minus gamma minus 1 over 2. So this is the normal shock wave relation which we have for calculating the Mach numbers ahead and downstream of the normal shock wave. So let's apply or substitute the values what we know, that 0.4 over 2 times 2.36 squares. That we did not calculate this 2.36. How we got this 2.36 means that M1 component N, that is normal component, equals to Mach number 1, that is 3 times sine of the angle is 52 degrees. You will get 2.36. This is the Mach number normal to the oblique shock wave. So let's substitute the remaining values as gamma equals to 1.4 times 2.36 square minus gamma equals, this is 0.4 over 2. So these are the values that we obtained from normal shock wave relations, and we substituted that. Then upon simplifying this, you will see 2.11 by 7.60 equals to 0.28. So again, we need to clearly see that this is not, yeah, M2 is so M2 is equals to square root of 0.28. We can clearly see that this is less than 1. It is always, you should clear that for the oblique shock wave, it is not necessary the flow to be subsonic. If it is flow is supersonic and crossing the oblique shock wave in the downstream, it is not necessary that flow should be subsonic. But there is component normal to the oblique shock wave, the Mach number should be subsonic in this way. That is M2. Then it is the same thing that we obtained here. That is M2n is square root of 0.28, that is less than 1. So it is now subsonic. So we are in the right track. So what we need to do is, again, we need to transform this into the component that is M2. We need to transform or we need to resolve this into M2. So how we can resolve that? At M2 is equals to, from the trigonometry again, M2 is equals to Mn2 comma, so Mn2 upon the sine of beta, that is shock wave angle, minus theta, that is wedge angle or the compression corner angle. So let's substitute the details what we have. We already obtained that Mn2, that is normal component, as 0. Square root of 0.28, and then sine of the oblique shock wave angle is 52 degrees minus 30 degrees. For doing this, we will get the M2 as 1.3, which is supersonic. So you see, as I just stated earlier, that it is not necessary that oblique shock wave to generate a subsonic flow. It can be supersonic also. So for this Mach number M1, if it is traveling or passing through a oblique shock wave, which generated by a compression corner of 30 degrees and the oblique shock wave angle is 52 degrees, the M1, which is earlier as 3 Mach number, will transformed into M2 of Mach number of 1.3. Both are supersonic. So this is the solution of this problem. So with this, we come to the last question of this particular presentation. And still we have some more time. So I will just start few questions from the next presentation. Then we can end this session. So far, yes. Okay. So far, so good. Let's go to the next presentation. So the session questions that now we are seeing is related to your week 10 course content covered by professor, and we will see some of the questions that related to that content, and the questions are like this. So in our first question, we have like these are mostly in experimental aerodynamics, that all these questions are related to experimental aerodynamics. So these questions can be mostly theoretical, and some questions can be experimental also based upon the instruments that we see. So let's see the first question. The following visualization images from left to right represent. So we have some images here representing the flow features on on different objects, and now we need to say whether what kind of flow visualization is this. The first one we can say this is an oil flow visualization. This is an oil flow visualization, and the second one is a smoke flow visualization, and the third one is stuffed flow visualization, where we arrange the threads kind of structure on the top of the airfoil surface, and we will see the pattern of the fluid flow movement. This is a kind of a flow visualization, and the last one is dye flow visualization. Dye visualization. The things that I have to mention is we can do the oil flow visualization either in water tunnel or wind tunnel. This can be done any kind of flow media, like the fluid can be water or the fluid can be air, can create this kind of oil flow insulation. But the smoke flow insulation we can do only in the wind tunnels, allowing the smoke on top of the object or inside the wind tunnel. We can allow some smoke, and that creates this kind of smoke flow visualization. Coming to the tough flow visualization, also we can do in any oil flow or what airflow or water flow, but in tough flow visualization is mostly preferable for wind tunnels only. And the dive flow visualization, again, we need to use the water tunnels. Okay, so a type of flow visualization is also necessary to understand, like if we want which kind of characteristics we want to visualize. Based upon that, we need to use our instruments. Where the first one is the oil flow visualization. It is good for only the surface flow characteristics, but not for uh, the details on top of the flow physics, on top of the fluid object. You can only give the separation lines or uh, the strong separation and reattachments when you do the oil flow visualization on any object, that it won't give the any structures that is above the object that we are studying, the flow structures above the object that we want to study. But the smoke flow visualization has this capability that it can give the details not on the surface but on the object. But as we can see here, it can give the details. This is what actually we need to understand. In compare both, we need to understand on the surface flow features, on the near body flow features. Also, we need to understand to get the complete picture of the flow physics happening around the body, where the tough flow is also restricted to the surface, but it can also give some good physics from this visualization. And in the same way, dive flow visualization. So the correct option for this is a oil flow, smoke flow, tough flow, and dive visualization. Okay, so let's go to the next question. And yes, here we have some question related to. You can see a pitot tube here. It is a question related to the pitot tube. Here, air flows from a reservoir through a converging diverging nozzle. Air flows from a reservoir through a converging diverging nozzle. Let's draw the reservoir again. We already drawn the reservoir in the previous presentation. So let's draw the same reservoir, and we have a convergent divergent nozzle here. So this convergent divergent nozzle, we are having a pitot tube. We are having a pitot tube. Assume this is a static, but not pitot static tube. So we are now measuring the static tube. So the point that did not mention in the question, we are now measuring static pressure here. So as we are measuring the static pressure, starting from just exit of the nozzle, that is in the height wise, we are keeping this. They assume this is exactly at the center of the nozzle, but not at the uh, bottom as I drawn. I think if it is better, I just draw again. So this tube, pitot static, the static pressure measurement we are doing using this pitot static tube for this problem. So as we are measuring the static pressure, starting from the end of the or exit of the nozzle and placing this probe at the midsection, that is from the height, in terms of the height you are placing at the midsection. So how this pressure, the static pressure that is measuring by this tube when we connect it to a manometer or something, any pressure sensor, how it actually behaves. because it is now like, or we should know about what is the flow happening inside. We just connected to a reservoir, whether it is subsonic, completely subsonic, or completely supersonic, we don't know. So, but so that purpose, they gave the given condition that it is entirely low subsonic speed. It is completely the low subsonic speed. So now this measurement is starting from here, and we are traveling from this point to the completely to the inlet of the from the for this particular portion or the exit of the reservoir. So how the pressure actually varies, that is taken by the manometer. If we see this pressure, because it is completely subsonic, you will have a high pressure, because it's a subsonic flow. When you expand, you will have high pressure at this particular location, and that pressure uh, is in this form. It is a question asked in the reverse way. So this is the entry, and this is the exit. This is pressure P static. So at the inlet, you have some value that is P reservoir, that's a P naught. And this P naught cannot be, so if it is a static pressure, like this, you will get. So you're having a stagnation pressure here, and that will reduce to minimum value at the throat section. This is your throat section. If this is your exit section, your pressure increases from the throat because it is subsonic flow. So if it is supersonic flow, the picture is reverse. Okay. The supersonic flow, we already discussed that particular kind of pattern uh, previously several times, like how the pressure versus velocity actually varies in a supersonic flow. For the supersonic flow, if it is we are providing any kind of expansion area, the pressure and the velocity always increases for the supersonic flow. But in the subsonic flow, if we are providing any expansion or diffusive kind of area, this is the diffusion section or the divergent section, I can say, not the diffusion, diverging section. So if you are providing any divergent section for the subsonic flow, the velocity decreases and the pressure also increases. So that is the thing happens for the subsonic flow. So it will decrease first. So this is the option, correct option. So it will decrease first up to the throat and then increases up to the entry. Okay, this is the picture of how this pressure varies through along the nose. Okay, let's go to the next question. So here we have some manometric kind of question that we are seeing now. So let me read the question for you. So in this question, we have that mercury is used as a manometric fluid. We are having the mercury as a manometric fluid in this uh, for this setup of experiment in the manometer. It's a manometer used for the pressure measurement in the supersonic winter. You know, it is a flow is a supersonic, and we have wall static ports. Note that the wall static ports from two different points in the wind tunnel. I will just draw the test section for you better understanding. Say this is your test section, and you will get a convergent divergent section. That's the difference. So let's assume only the this is the supersonic test section, and you have a ports here. This is the manometer that contains the mercury, and the ports that you are connected from two different points from the wall static pressure from one and two different points, and two limbs, these two liquid columns, we get a difference of around 2 centimeters. So this particular difference is around 2 centimeters, which is huge. When you see the manometer liquid is mercury and 2 centimeters of difference, this is relatively huge difference. When we compare the same with the water, you will get very high difference because of this gravity difference, the specific gravity or density differences. So we know that already from the standards, the specific gravity of the mercury is 13.6. When you convert into the density, with respect to the water, you can use that water density for converting into the density. And the question is, calculate the static pressure differences in pascals between these 2 points. We need to find out the static pressure difference between point 1 and 2, as there is a difference in height of the liquid column that is around 2 centimeters. Definitely we get a difference of some value between these two locations that we can calculate just directly by using that del P, the difference in the pressure, is equals to rho G P H or rho G del H. That is the correct presentation. Rho G del H. So what is our rho? Rho is 13,600 because our specific gravity is 13.6 times the density of water is 1000. That will give you 13,600. So the density is 13,600, and you can use the gravity as 9.81 times the difference is 2 centimeters. So 2 centimeters I can write as 0.02 meters. So this is a simple problem that we are discussing. Simple problem to just finding out the pressure differences between 2 points in a supersonic interval. You can use this direct del P equation. And then once we do that, we will get the difference of around 2,668 pascals, which is significantly so high. It's around, I can say, 2 kilopascals or 2.6 kilopascals. 2.668 kilopascal. This is a significantly huge value high power in the supersonic intent. I have to mention one more point here. Why we are using the mercury instead of water for the supersonic kind of behaviors? Why not any other alcohol or spirit or some other kind of fluid, manometric fluid instead of this mercury? So because when we are dealing with the supersonic flows or very high pressure differences kind of requirements, the mercury has a specific gravity around 13.6 when compared to the density, or you can say the density ratio or the density of the mercury is so high. So the height differences it creates, or the equipment needed, or a YouTube height that it needed for the same pressure difference is very less comparatively. If you use any water, you need a very big manometer tubes to measure the same 2 kilopascals. So that is the key reason, the first reason that why we are using the mercury uh, for this particular kind of experimental setups when there is a huge pressure differences. So with this, we have a few more questions in this presentation that we will discuss in the later on sessions. Yeah, these are all the questions that we will cover in the later on sessions. So if you have any doubts so far, we can discuss that, or else we can end this session. See, just come out of the screen. So if there are no doubts, just we can discuss today. So thank you everyone for joining today. Have a nice weekend. We'll see you in the next week. Thank you all.